Hello, Earth Science class, and welcome to online lecturing of Chapter 1, An Introduction to Earth Science. You might be wondering, what is Earth Science? Well, Earth Science includes a lot of different sciences together that help to understand our Earth and our distant neighbors. So this includes astronomy, meteorology, geology here on Earth, and oceanography. Okay, here's a really cool image off to your right. This is what we call Earthrise right here. And this was the first image taken of our Earth in its entirety from the Apollo mission in 1969, Apollo 8. So the astronomers were kind of bouncing around the moon, and their job was to take pictures of moon rocks. And they got kind of bored, and they looked up and they went, oh my God, all of Earth in its entirety rising up, much like the moon kind of rises in its various phases on Earth when we see it, but on the moon they see Earth rise, which is pretty crazy. It's a huge paradigm shift in the understanding of our Earth as a kind of a whole system without boundaries from countries and stuff like that. So, pretty amazing picture there. So Earth science includes geology, that's the study of the Earth. There's physical geology and historical geology. Historical deals with Earth history through time, with evolution of organisms, as well as history of the different environments on Earth and the different rocks we find in them and fossils and all that. Physical deals with hydrology, volcanism, earthquakes, plate tectonics, faults. Okay. Then there's oceanography. That's the study of the ocean. We're really a water planet. 70% of our surface is covered by the oceans. So our Earth is, we call it Earth, but we should really call it like Oceanus. Okay. Then there's meteorology. That's the study of the atmosphere and the processes that produce our weather. And then astronomy is the study of the cosmos. Earth science is also environmental science because a lot of the natural hazards that occur as a result of geologic phenomenon affect humans on Earth, whether it be landslides, hurricanes, earthquakes, tsunamis. Those are all events that have occurred throughout geologic time and will continue to occur in our lifespans, so we have to deal with that. In addition to that, humans need resources to survive, and the Earth provides those resources, whether it be different types of ore, or metals, gold, copper. Here's a mine, okay, and other resources like fossil fuels, which can, the burning of coal can smog up the surrounding metropolitan areas. And so what we have to understand is that we're part of this system. We're not separated from the Earth. Anything we do on Earth will affect other organisms, other environments, and ultimately the entire Earth as a system. And in Earth science, when you take an Earth science class, you got to understand the scales of space and time. Geologic time, whenever I bring that up, I'm talking about millions of years time of the passage of time on Earth. And that's hard to kind of understand because our time scales in terms of our lives on average are what, 70 to 80 years. It's difficult to imagine what a million years or how long that actually is. Humans or Homo sapiens have been around, our estimates are about 2.1 to 2.5 million years that they've been on Earth. So that's not a long time. A billion is 1,000 of those million years. So a billion years is a really long time. And so a billion is a very large number. And the Earth is 4.6 billion years old. Almost 5 billion years old. A billion is a really large number. I really suggest going on YouTube and YouTubing how much money Jeff Bezos has in terms of grains of rice, and they do a good comparison of a grain of rice that is equivalent to $100, and then showing how much money Jeff Bezos from Amazon has amassed, and it's a big pile of rice. And just to get an idea of how much a billion actually is. Okay, the Earth is really old, is what I'm getting at. 4.6 billion years, and that's confirmed through age dating of meteorites that have fallen on Earth. All of them come up with the same date. Meteorites are believed to be the kind of vestiges of planetesimal material during the formation of planets in the early solar system. And they come up with that age consistently. The oldest rocks on Earth are between 3.5 and 3.8 billion years old. Moon rocks are about 4.2 billion years old. So yeah, Earth has been around for a really long time. And so what geologists have done through over the course of the past kind of 200 years is develop a geologic timescale, and that kind of divides Earth's history in kind of meaningful units, major developments, and here it is. Okay, this area down here is the majority of Earth time. This is about 4 billion years. 4 billion years, where we believe the earliest direct evidence of life occurred 3.5 billion years ago, single-celled bacteria in the ocean. And so the Earth was a very lonely place. Remember, bacteria aren't visible, so you wouldn't be able to see them. Although these are stromatolites, which create these layered mounds, so I guess you could see those. Anyways, but the first evidence of more complex life with hard shells in the oceans occurred around 541 million years ago. And that started the Phanerozoic eon. Okay, and then here, if you have time, you can zoom in and take a look at all the major geologic and life developments through Earth time as figured out by finding direct evidence from fossils and other kind of indirect or proxy evidence, which is, it's kind of cool watching the evolution or the fossil assemblages change from invertebrates to vertebrates to fish to amphibians to reptiles to insects and birds than mammals. Okay, early primates showed up around here. All right, so this is the geologic timescale breaking down individual time periods in Earth's history. A lot of times the reason why there's a major change or a division in Earth's history is some major geologic event, asteroid striking Earth, major volcanic eruptions, or anoxic events in the oceans. These are all, or major mass extinctions. These are all major events that have occurred in Earth's past. So the nature of scientific inquiry, whenever you take a science class, is that science assumes the natural world is consistent and predictable. And with that in mind, the goal of science is to kind of figure out that pattern, figure out the phenomenon that occur and try to predict what's going to happen next. And they use knowledge and data collection for those predictions. And the way they go about doing that is through observation and measurement. Okay, here is a paleontologist on the outcrop side of a mountain collecting fossil data. This person may find a new species of a new discovery, a new organism that had existed in Earth past, and be able to add it to the geologic timescale, essentially. So those are how discoveries are made. A meteorologist, for example, may use wind speed, relative humidity, air temperature to give a daily weather report, and that's directly measuring the conditions of the atmosphere in this area. And so the way scientific inquiry works is scientists typically come up with an idea, and they develop a hypothesis. And a hypothesis is a tentative or untested explanation for something that may have occurred. And a cool example of this is looking back about 66 million years ago at the KT boundary. That was the boundary between our current Cenozoic era and the end of the Mesozoic. And here, what paleontologists long knew was that the dinosaurs went extinct. You find dinosaur fossils in rocks that are older than 66 million years, and you no longer find those large reptiles and any rocks that are aged younger than 66 million years. So for a long time, paleontologists were perplexed about what happened to the dinosaurs. They know they went extinct, but what could the possible explanation be? So they developed a number of hypotheses. Perhaps there was a major Earth cooling event and there was an ice age and dinosaurs couldn't handle that. Maybe the oceans became anoxic, lost a lot of oxygen, became major dead zones, and that kind of cascaded the kind of trophic levels in the marine environment, and that led to things dying on Earth. Maybe there was a major volcanic eruption spewing out CO2 in the atmosphere, warming it up, killing a lot of the plants, and dinosaurs went along with it. And maybe an asteroid struck Earth, and that caused a cataclysmic event that kind of put an end to the dinosaurs. So those are all different hypotheses. All right, and there was a group of scientists called that made up we'll refer to them as the Alvarez team, and they're the group of scientists that eventually came up with the Alvarez Theory. And a theory is a tested and confirmed hypothesis, and that's a hypothesis where it's been rigorously tested. Okay, so the Alvarez Theory is the kind of consensus best explanation on why the dinosaurs went extinct, and that's the theory that an asteroid struck the Earth 66 million years ago. And the way the Alvarez team came and developed that theory is through the scientific method, and that process I'll show you in the next slide will show you kind of a logical procedure to follow to help use data collection or laboratory results to come up with useful conclusions. Okay, and that's how you formulate hypotheses and then eventually theories. A paradigm is when a theory explains a large number of interrelated aspects of the world. This is typically kind of like a major theory. You can think of theory of evolution, for example, or the theory of plate tectonics, which we'll cover soon. Okay, those were major paradigm shifts in the scientific community. All right, and so here's a depiction of an asteroid striking Earth, artist depiction. And then here's the KT boundary. Okay, so this boundary right here is the division between older rocks below, part of the Mesozoic, where you would find fossils of dinosaurs. Okay, and then up here is anything younger than 66 million years. So here are the steps in the scientific method. You raise a question about the natural world. Why did the dinosaurs go extinct? Do some background research, which the Alvarez team did. They found out the numerous ways that organisms can go extinct, all the different scenarios, and then they construct a hypothesis to explain why that occurred. And here you can create more than one hypothesis, because there could be more than one reason why the dinosaurs went extinct. Okay, and then here's the key: you develop observations or experiments to test your hypothesis. So that's what's critical in science, is that you come up with, or you construct a hypothesis, and then you're supposed to test it. And the purpose of that is to find out whether or not the hypothesis holds up. Okay, so what the Alvarez team did was they collected a bunch of samples at that KT boundary from different parts of the world. And what they analyzed the rock and paleo sediment from that, specifically that boundary, and what they found was there was this metal that was anomalously high in terms of its concentration, specifically at that boundary, and that metal is iridium. Iridium is found everywhere. You can find it in soils and stuff like that, but in very low concentrations. But for some reason, right at this KT boundary, it's in really high concentrations. And they found that in all of their KT boundary samples, this was true, that there was this iridium anomaly. So they analyzed the data. Okay, so after they analyzed the data and took a look at that iridium anomaly, what they noticed is that meteorites actually have high concentrations of iridium. So asteroids coming in and, into Earth's atmosphere, eviscerating and then hitting the Earth's surface would just absolutely pulverize the crust of the Earth, anything in its way, and also pulverize itself. And it would basically shoot up a lot of ejecta into the upper atmosphere. So a lot of this iridium would go up in the atmosphere, then kind of be carried by atmospheric circulation across the globe, and then deposit in all the environments across the globe. And that's how that iridium could spread around the entire world 66 million years ago when that occurred. So those results supported their hypothesis that an asteroid was the reason, an asteroid impact, and that cataclysmic event was the reason for the dinosaurs going extinct. However, it's still not foolproof yet, right? Other scientists also want to test that hypothesis. The Alvarez hypothesis hadn't become a theory yet. So other scientists with KT boundaries from different parts of the world were like, hey, let's check for this iridium anomaly. So they go back and they run the scientific method again and get the results and determine whether it supports their hypothesis or doesn't support the hypothesis. And what they found was, yeah, there is an iridium anomaly in all those samples that they could retest. So that was good. But the thing is, a lot of scientists were still skeptical because it was like, hey, all right, if there is this iridium anomaly, but where is the crater, right? That would be like the smoking gun kind of direct evidence that an asteroid struck the Earth, right? And the Alvarez team, they didn't know where the crater was. They had no idea. They thought it should be somewhere, right? It could be in the middle of the ocean, for all they know. But a group of geologists from an energy company alerted the Alvarez team about an interesting structure in the Yucatan, near the Yucatan Peninsula in Mexico. And so they went out there and collected some rock samples to age date them to see how old they were and if indeed this was a crater rather than maybe just a basin. So they raised that question again, did some background research, and analyzed the data, and sure enough, it was structurally a crater, and the rocks that were age dated there came out to 66 million years ago. They also found kind of micro diamond impact evidence, which indicates that there was an asteroidal impact there, and that supported their hypothesis. So through that rigorous testing, now their hypothesis becomes a theory, and that's the Alvarez theory, and that's the kind of consensus scientific explanation for the fate of the dinosaurs 66 million years ago. Okay, so let's move on to the evolution of our Earth. We have to start with the universe beginning, the Big Bang, 13.7 billion years ago. That's what created all matter, and that matter kind of just started to disperse in the expanding cosmos. And anything that has mass attracts other mass because of gravity, and those clumps of material started to form the very first galaxies. Okay, and initially, the materials early on in our universe, our expanding hot universe, really the elements that were just present were just hydrogen, helium, and lithium. That was essentially it, really light elements. But what those things started to form were the first galaxies and the first stars. And in stars, these are massive objects in space. In the cauldron of the center of stars, there's thermonuclear fusion, and new elements are created, heavier elements like oxygen, carbon, okay? And then through the lifespan of a star, depending on their size, they could swell up to a red giant or even supernova. And if there's a supernovaing star, new elements are created. And that's how it kind of generates the heavier elements in our periodic table. So our sun, our star is considered a third generation star, meaning that there were two previous stars that formed, lived, died, collapsed, spreading their newly created elemental guts into interstellar space to form a new star. And that's the reason why we have heavy elements present on Earth. It's because of those lifespans of previous stars that had existed. Okay, so our sun is found in the Milky Way galaxy, spiraling galaxy, like what you see here. Interestingly enough, we're on like one of the outer arms, and we're spinning in a counterclockwise direction along the outer arms. It takes about, 237 million years to do a full revolution around the center of our Milky Way galaxy. And it's big. Our galaxy is very big. The diameter of our galaxy, so if you were going from one end to another, so from like here to here, straight line, it would take you 100,000 light years. If you were going the speed of light, it would take you 100,000 years, or in terms of distance, it's 100,000 light years of distance. So yeah, that's huge. And that's just one galaxy. We have billions of galaxies in our expanding universe. Okay, so our solar system began to form in one of the outer portions of the Milky Way galaxy. And the Earth and other planets began to form at the same time. We formed from a giant gas cloud called a solar nebula. Okay, and so what this was is just essentially a huge cloud of mostly hydrogen and helium. There were a lot of dust grains of heavier material, silicate material, rock, really small grainy stuff surrounding in this cloud. But like I said, anything with mass starts to attract each other, then they start to clump together. And at the center of this cloud is our proto-sun. And this once kind of three-dimensional nebulous cloud started to flatten and rotate and start to spin and generate heat. And at the center of that is our proto-sun, the largest celestial object in our solar system. Okay. And so what occurred here, the sun began to become larger and larger and then start to produce heat and sunlight. Started that thermonuclear fusion process. And surrounding our proto-sun, material started to coalesce and collide with each other. And this was the formation of our first planetesimals. So the four rocky interior planets, Mercury, Venus, Mars, and Earth, they're closest to the sun, and so they're rocky planets. The reason why they're rocky is because the heavier material was able to condense from the really hot proto-sun and condense closer to the sun. And then all that material started to orbit the sun and then collide and coalesce with other small bits of planetesimals, kind of making these planetesimals larger and larger. Okay. Then there's the belt out here. This is all former planetesimal material that didn't coalesce to form a planet. Okay. And then as you go further out, then you start running into the gas giants. And the reason why you see the gas giants really far away is because this is where it was a little cooler and the volatile elements and the gases were able to condense a little further away where it was cooler. And that's why we have mostly gas giants beyond the asteroid belt here. Okay, so that's the nebular theory. So our solar system evolved from that kind of condensing, rotating cloud of gas about 5 billion years ago. Like I said, the inner planets are metallic and rocky clumps, and then the outer planets kind of form fragments of ice. Interestingly enough, like Saturn is less dense than water. So if you had an ocean big enough, you could actually, Saturn would actually float in it. It's pretty crazy. Okay, Earth has a layered structure. And so as the Earth kind of slowly formed, initially this is how the planetesimals kind of grew in size, all this material kind of coalescing and colliding with together. Early Earth was really hot because of all these collisions, because of the radioactive elements, especially the short-lived ones, released a lot of heat. It basically melted the entire Earth. And when you melt a well-mixed substance that has like gas in it, or that has metal in it, that has silicate rock in it. These materials tend to start separating from one another when they reach their melting temperatures. And so iron and nickel, the heaviest material of our planet, began to sink towards the center. Okay, and then the lighter rocky components started to float outwards towards the surface. Gaseous material escaped the kind of molten surface of the Earth to become our very primitive atmosphere. It's mostly carbon dioxide, methane, and nitrogen, with some water vapor. Okay, but that's how kind of the different layers of our Earth began to form. Okay, it's kind of like when you say you boil milk. I don't know if you've ever done that before, but if you notice the cream or the skim, the lighter stuff will float to the top. That's because you're heating up that milk, so you start segregating materials based on density. All right, here's a cool way to look at our solar system. Okay, our sun is absolutely huge. Okay, in terms of scale, this is our sun in comparison to the 4 interior rocky planets right there. There's Jupiter, Saturn, Uranus, and Neptune. Those are huge gas giants in comparison to our small interior rocky planets. But all, when compared to the sun, that's the Earth, that little blue dot. The sun is absolutely massive. So our Earth is a system, as those kind of astronauts took a picture of our Earth in its entirety from the Apollo mission. The Earth is made up of separate interacting parts that define our dynamic Earth system, which makes it very complex. The hydrosphere is a component of that system. That is the ocean. All right, it covers 71% of the Earth's surface. It contains 97% of the Earth's water. It's all freshwater, streams, lakes, glaciers, as well as groundwater and biological water, right? So here it is. This is all the water on Earth. It's mostly ocean water. This small 2.5% is fresh water, okay? But the majority of this is locked up in ice sheets and glaciers, so not very accessible to humans. And then the rest is groundwater, and just a little bit is all the fresh water. So all the rivers, all the lakes, all that only makes up 0.03% of all the water on Earth. So the Earth is big. Then there's the atmosphere. That's another component. This is kind of a thin blanket of air that surrounds us. Okay, it's about half of it lies 3.5 miles above the Earth's surface. So that's right here. Okay, this is Mount Everest, for example. So if you've ever seen any of those documentaries or anything about anyone climbing Mount Everest, you always see that they have like oxygen tanks when they get close to the summit, and that's because the majority of the atmosphere is actually below the summit of Mount Everest. So there's very little oxygen to breathe at those altitudes, and that's very dangerous for those hikers. Okay. Then there's the biosphere. This includes all life. You and me, our pets, coral reefs, rainforests, all the bacteria, fungus, plants. All that material is concentrated near the surface, and that's the biosphere. The geosphere is the solid Earth, by far the largest of all the spheres. It extends from the surface to the center of the planet, and there are compositional differences in the different layers in the interior of the Earth. There's the crust, which is the outer layer, mostly made up of very light silicate rocks. The mantle is also rock material, but it's just a little heavier, has more iron and magnesium in it. And then the core is made up of iron and nickel. Okay. And then we also divide up different layers of our Earth based on how the material behaves, rather than just chemistry. Okay, so for example, here's the crust. It can be anywhere between 7 to 70 kilometers thick. The mantle is almost like 3,000 kilometers of high density rock. Okay, and then here's the core. This is iron and nickel. So those three divisions are based on chemistry. Crust is low density rock, mantle is high density rock, and the core is just iron and nickel. But we can also divide Earth's layers in terms of how the material behaves. Okay, the outer layer we call the lithosphere, and this is material that is solid and rigid, and it's on average 100 kilometers thick. It behaves rigidly, meaning like it can break. Like if you have a ruler or a pencil and you bend it and it snaps, that's rigid behavior. Below the lithosphere is the asthenosphere. This is still a solid, but it behaves plastically. It's very mobile. It's kind of like clay. You know how you can like shape clay into something, or Play-Doh into a new shape? It's very plastic and mobile. Okay, that's the asthenosphere. Okay, and then once you go into the lower mantle, it becomes rigid again, and then the outer core of our Earth is actually liquid, and then the inner core is solid. That's solid iron and nickel. So those are the Earth's layers based on two different properties: how it behaves and its chemistry. And each of these spheres that I've mentioned before are linked together, and another one, so it's all really connected. Okay, and when there are people on Earth, you know, we're burning a lot of coal, we alter the atmosphere, and that can alter the oceans, and so forth. And the hydrological cycle is a way to show these interactions, right? How water molecules kind of move through all the different spheres. From the hydrosphere in the ocean, water evaporates, condenses to form clouds, and then that stuff rains onto land, snow or rain, and that water can run off into lakes and into rivers back into the ocean, can be used up by plants and returned into the atmosphere, or just infiltrate and become part of the groundwater system. Okay, so let's talk about what's on the Earth. What's the face of our Earth, meaning like the different major geologic regions. We've got the ocean basins. These are the lowest lying areas on Earth. They're typically, on average, 2.8 miles below sea level. And what we find there are basaltic rocks. Basaltic rocks are a volcanic rock that's black. Okay. I'm not sure if I have a picture in here, but these are kind of volcanic black rocks that form typically on the surface of the ocean basins. On the continents where humans live, these are relatively flat areas, typically only about half a mile in elevation above sea level, and they're made up of granitic rocks. And granitic rocks or granites are like the, I don't know if you've seen or watched HGTV where people are like, I want granite in my kitchen. And they look at those countertops. A lot of times that's granite. It's kind of like this speckly, hard rock material that's polished. Okay. Well, I mean, if you find it on the Earth's surface, obviously it's not polished, but it's a low density volcanic rock as well. Okay. So here you go. These are the major ocean basins. Here, Pacific Ocean Basin, low-lying areas where you find a lot of those basaltic rocks. And then here on the continents, you typically find a lot of those granitic rocks. So these are the continents. So let's talk about the major features of the ocean basin. The continental margins are areas that are right next to the ocean basin. So they're the margin of continents and the ocean. And so there's the continental shelf, which is this region right here, this flat-lying area here. It's really just the portion of the continent that's flooded by the ocean. Sea level rises and falls through geologic time. In past time, sea level has been 600 feet lower than it is today. So Florida kind of doubles in size, and a lot of the continental shelf is exposed to the air or above sea level. And another time, sea level has been over 300 feet higher than it is today, and most of Florida would be submerged. Okay, so the continental shelf kind of varies in thickness, and also in terms of geologic time, how wide it is or how much of it is exposed. So this is just a gently sloping area right here. Okay, the slope is just after that. There's a huge drop off here. This is the continental slope. Okay, the rise is this area here, and the rise is where a lot of material is dumped out into the deep ocean from land typically. So a lot of the rocks found here weather into small sediment like sand and clay, and that gets carried out by wind or water down to these deep areas of the ocean. And you can have huge piles of sediment here. We call it the continental rise. Okay, and then when you get into the deep ocean basins, beyond the continental rise, you have abyssal plains. These are these flat-lying areas here in the deep ocean. These are the flattest, some of the flattest places on Earth. What you also find are deep ocean trenches. So that's right here. You see that trench right here? You can see that's a trench. What's going on here is that there's actual portion of the ocean crust is subducting into the mantle. So it creates these deep scars at the bottom of the oceans. These are the deepest parts of the ocean basin. Okay. And then in these areas, typically on the abyssal plains, you'll see a lot of abyssal hills or seamounts. These are just volcanic features that are found all over the ocean floor. And what you'll find a lot too are these mid-ocean ridges. These are areas of intense volcanism where two plates are kind of moving away from each other. So that's in the deep ocean basin. Here we go. Here's an ocean ridge. This one goes right through Iceland, goes right through the center of the Atlantic Ocean basin. So over here, you can see the Lesser Antilles. Okay, here's Cuba, here's Florida, Puerto Rico. Yeah. Here's an ocean trench, and this is a mid-ocean ridge. These are more shallow areas of the ocean because of the intense volcanic activity. So there's also, we find them in all the major oceans. There's some in the Pacific and in the Indian Ocean. And essentially, it's a mountain chain. It's a mountain chain at the bottom of the ocean. We didn't know they existed until we started mapping the ocean floor in like the 50s. And they're just many layers of igneous rocks. And their formation is from volcanic eruptions that occur at the bottom of the ocean. Okay, so let's talk about the major features on continents. We've got the major mountain belts. Okay, most of them are part of the Circum-Pacific Belt or the Alps Himalayan Belt. There's also some stable interior areas. We refer to them as shields. These are flat regions of deformed, really old crystalline rock. And then stable platforms, which are sedimentary rocks that cover the crystalline rocks. Let's show you a picture here. So anywhere in yellow that you see here are considered a young mountain belt. That's 100 million years old or less than that. So the Andes Mountains and all the Cordilleran mountains that run through the West Coast and Central America. So all of these are considered young mountain belts. And this is what you would typically see in those regions. Okay, this is a picture from the Himalayas. The Himalayas are the most majestic and youngest mountains on Earth, so they have the highest elevations and really incredible. So that's this beautiful picture here. But this is part of the Alpine Himalayan mountain chain. Okay, so these are all relatively young mountainous regions. Okay, then there are much older mountains. The Appalachian Mountains start from kind of northern Georgia all the way to Newfoundland or Maine, and the Caledonian Belt, which is related to them, the Urals, okay, some older mountains in Greenland and northern Canada, as well as Australia. These are mountains that can be older than 300 million years old, for example. So they've been on Earth for a really long time. So they've slowly kind of eroded down into a more subdued topography like you see here. This is typical of the Appalachians with trees kind of growing over the ridges here, and it has a kind of subdued view. That's over geologic time, millions of years, these rocks are slowly weathering away from surface processes like glaciers or rivers cutting through or rain and all the different weathering processes. And then here are the shields. Almost every continent has really old crystalline rocks, shields. Here's one in India, Australia, the Brazilian shield, and the Canadian shield. They look like these rocks, really old rocks. Some of them can be as old as 3.8 billion years old. And they're heavily weathered, exposed, kind of deep, metamorphic rocks that have been kind of been around for a long time on Earth. So this is what we typically see on the continents. And then the stable platforms where Florida is, these are areas that are covered by sedimentary rocks. Okay, and sedimentary rocks form from processes on the Earth. They're much younger than the shield rocks. Okay, so we have to understand Earth as a system. It's kind of an open system where energy can come in and flow out. The Earth consists of nearly an endless array of subsystems, hydrological cycle, rock cycles. And what really powers this Earth system are two things. One is the sun that drives a lot of the external processes like weather. When sunlight and solar radiation strike the atmosphere, that starts to heat up the air masses and causes them to rise and fall and move, and that's what generates our general wind patterns. Okay, also drives ocean circulation, evaporation. All that is directly from the sun. And another source of energy that kind of powers our Earth system and its complexity is the interior. There's a lot of heat that's conducting and convecting through the center of the Earth outward, and that causes a lot of movement. Okay, that causes a lot of the lithospheric plates to move at the surface of the Earth, and that drives a lot of geologic processes. So volcanoes, earthquakes, and mountain building, that's directly related to heat being driven through the different layers of Earth. And so we got to understand we're part of that system. Okay, here are those two sources, right, volcanism and the sun. And that concludes our first lecture.